Okay, this is our trig review number 6, which is focusing in particular on the conversion from rectangular coordinates to polar coordinates. So we think rectangular coordinates are x, y, Cartesian plane, and polar coordinates are r, theta. And as I alluded to on recording number 5, we noted that this is very closely related to the idea that x, that the cosine of theta was x over r, and the sine of theta was y over r. And we also had the tangent of theta was y over x. But let's investigate these things just a little bit more closely. Let's consider theta in the first quadrant, quadrant 1, and we have our ordered pair xy, and this does not have to be on the unit circle. This is the x value here, this is the y value here, and our angle is in standard position, so I'll run it this way. There's theta. Okay, if we extract this diagram off to the side here just a little bit, you'll note that this is x, this is r is the radial value away, and then the y value, which I marked here on the y-axis, we can just slide over and put right here, so that the third side of our triangle, right triangle, becomes y. And this certainly makes perfect sense. X is a horizontal distance, y is a vertical distance, and r is a radial distance, and there's our angle theta in standard position. Okay. Now, consider our right triangle definitions that we had way back in video number 1. We know the cosine of the angle is adjacent over the hypotenuse. We had the sine of the angle is the opposite over the hypotenuse, and the tangent of the angle was opposite over adjacent, y over x. And these are the exact same definitions we had in recording number 4. So these are the definitions of the 3 trig functions, right, working out of this triangle. Now, polar coordinates. Let's take any one of these equations. We'll take the first one, the cosine of theta is x over r. Here's our right triangle. There's theta, there's x, there's r, there's y, and we see very clearly the cosine of theta is x over r, but multiplying both sides by r, we get the equation x is equal to r cosine theta. And this will be one of our conversion equations in polar coordinates. Likewise, same triangle, but now let's consider y and r and theta. So we have the sine of theta is y over r, or y is r sine theta. That'll be our second one. Both of these equations are used when converting. Let me just note this off to the side. This is converting an r theta pair to an xy pair. Quick example might make that. Let me pull up a new screen here. Let's suppose we had an r theta given, and I'll choose a rather simple one. Let's suppose we have 3 as r and theta is pi over 4, and somehow we got to convert that to an xy pair. Okay, so let's think about what this looks like graphically. This is a point. This point here is 3 units away from the origin, and the direction is pi over 4. So pi over 4 is our 45-degree angle, and we're stepping 3 units away. 1, 2, 3. If we had a polar grid, you can imagine this would be our unit circle, 1 unit away. This is a slightly larger circle with radius 2, and the one we need is radius 3, and we're 4 units away, or 3 units away. So 1, 2, 3. Here's our point. In our theta world, this is 3 and pi over 4, assuming this radial line here is at an angle of 45 degrees or pi over 4. Okay, so the task now is to convert that information to rectangular coordinates with x and y. Now, you can do it all algebraically. Again, we've seen this before. This is our circle. We have x squared plus y squared is 9. And we have this line, y equals x. Okay, y, that's a 45-degree line. And we have this point. And our task is to figure out what x, y. You could solve this system of equations. That would be an algebra approach. So there's a quadratic, has the circle, and here's a linear, which gives you the line, and solve that system of equations algebraically, and you'll come up with the solution. Actually, there'll be two solutions, one where x and y are both negative, but we obviously are in quadrant 1 here, so we want x and y both to be positive, bigger than 0. So if you like algebra, have at it. But I'm going to use my conversion formulas that x is r cosine theta and y is r sine theta. So this is sort of the trig approach, and you'll see it's actually much more efficient as long as the theta, this theta here, is one of our standard angles. So let's see. In this example, we're given r. R is equal to 3. Here's r, 3, and we're given theta, pi over 4, and that's a standard angle. So x is going to be r cosine of theta, pi over 4. And y is going to be r sine of theta, pi over 4. And because we know the sine and cosine of pi over 4, right, that's one of our unit circle things that we've memorized, we can easily write down the coordinates, the xy coordinates for this point. So the cosine of pi over 4 is the square root of 2 over 2. So we have 3 square roots of 2 over 2, that's the x. And the sine of pi over 4 is also square root of 2 over 2. So the y coordinate is 3 square roots of 2 over 2. There we are. And so we've solved this problem. We've taken this polar point and turned it into an xy point pretty easily. What happens if it's not a standard angle? Well, things are a little bit messier. Let's pick an ordered pair like, say, -3 and let's do 4 again. -3 and 4. And well, let's see. We want this is our xy now, and we're going to convert this to polar. We want to convert it to r theta. Okay, so here's our xy sketch. -3, 1, 2, 3, and 4, 1, 2, 3, 4. I'm telling you this is xy, so rectangular coordinates. There's our point. And now we need the r value, which is this distance, and we need the theta value, the angle. Okay. Unfortunately, the conversion formulas we have now, the ones that we've been doing, x is r cosine theta and y is r sine theta. These two formulas assume that we know r and theta and we're trying to get x and y. In this case, we know x and y and we need to get r and theta. So we're going to have to come up with two additional formulas. And let's go ahead and go back to our triangle again. This is theta, x, y, and r. And we noted that, that the tangent of theta was y over x. So I'll just write underneath that, using the arctangent function, theta is the arc that has a tangent of y over x. And then we're just going to have to put a little note there. Likewise, using our right triangle, we can use good old Pythagoras. We know x squared plus y squared is r squared. So r is going to be plus or minus the square root of x squared plus y squared. And you might question, why would r ever be negative? How could r ever be negative? Well, it really depends on what theta is. So if we go back to this diagram up here, if theta were positive, going out here to the second quadrant like that, then r would also be positive. But suppose theta was negative. Suppose theta was going this way. This is theta now. So if theta is negative in this case, less than 0, then R could not be positive. You would have to be backing up, if you will, backing up those required number of steps to get up to that point. Okay, again, here's my little unit circle. There's a circle of radius 2, a circle of radius 3. You can imagine there's a circle of radius 4, and this one up here is on this next circle. I guess I'm a little crowded down here, but you get the idea. Okay, so let's go ahead and take our point -3, 4 and convert it to polars. And we're going to be using these two conversion formulas. And here's where the note comes in. The arctangent function only returns angles in quadrant 1 and quadrant 4. You might want to remember, and we'll do this on another video, although I think we did this earlier in the year, that if you were to graph the tan inverse function, tan inverse of x, you noted that the largest it ever got was pi over 2. In fact, it never got to there. And the smallest it ever got was -pi over 2. -pi over 2. These were asymptotic behaviors here. And the graph looks something like this. If you remember, it was one branch of the tangent function inverted. So yeah, the angle is always going to be between pi over 2 and -pi over 2, which on the unit circle would correspond to quadrant 1 and quadrant 4 down here. So pi over 2 up at the top and -pi over 2 at the bottom. So yeah, going back to our problem here, this theta that we've got way over here, back on my polar grid, this theta is not going to work because the arctangent will not give us that. We're going to need, in fact, the theta down here in quadrant 4. So theta will be negative. Okay, let's see if we can go ahead and fit this up. We'll do the theta first. Theta is the arctangent of y over x, and for our problem, y is 4 and x is -3. So theta is the arctangent of 4 over -3. So theta tan inverse of -4/3. I really don't know what number that is. That's a non-standard angle, -4/3, like that. Tan inverse, or the arctangent of -4/3. My calculator could give me a good approximation. If I want the exact value, I'll just have to leave it this way, and note that that is going to be in quadrant 4. Okay, how about the r? R is much easier. We know that r can either be plus or minus the square root of x, -3 squared plus y 4 squared. So r will either be plus or minus the square root of 9 plus 16. R will be plus or minus 5. And in this case, we're going to choose the negative root. R is equal to -5. So now, you know, on a scale of 1 to 10, this is like an 8. This is a hard problem. So our xy -3, 4 converts to r theta as -5, and then the tan inverse of -4/3. Okay, r theta. Now, just as a double check, suppose I gave you, so you know, here's sort of like the Jeopardy question. I'll give you the answer, and you got to come up with the question. Suppose I gave you r theta was -5 and tan inverse of -4/3, and I wanted you to find now xy. And you go, oh, I have nice easy formulas for those. I know that x is r cosine of theta, and so let's see, x is going to be -5. That's my r. And now I need the cosine of the tan inverse of -4/3. Okay, so cosine of the tan inverse of -4/3. And so now you're going to have to, boy, this is reminiscent of one of our earlier test questions, where you're going to have to think of an XY grid, if you will. And we've got this -4. This is the Y coordinate. So you could think -4, 1, 2, 3, 4, -4. And the X coordinate is 3, 1, 2, 3. So here's my triangle down here, and this is my theta. Okay, so what would that be? I need the cosine of that angle. And we know the cosine of an angle is x over r. So x is going to be 3, and r is going to be 5. So the cosine of the angle is 3/5. So now we get x is equal to -5 times 3/5. And the 5's cancel, and we get -3, which sort of matches up with what we knew, right? X was, in fact, -3. Let's try y, sort of the same idea. We know y is r sine theta. And again, theta is this, the tan inverse. Let me grab another pen. This is what theta was. Tan inverse of -4/3. That's what we had calculated theta was. So y is going to be r times the sine of the tan inverse of -4/3. So once again, I can use that triangle there. This time, let me suppose the negative sign was on the bottom. It shouldn't matter, really. We'll put negative down there. Okay, so let's see. Now, here's our xy, and we got x to be -3, 1, 2, 3, and y is going to be 4, 1, 2, 3, 4. And here's our triangle. And again, I'll sort of put the triangle here. Now, notice that this angle theta is not really in standard position. So this might not be the best approach. So remember, standard position, we always have the initial side along the x-axis. You could use reference angles here and work this problem. But I think because we want the initial side to be along the positive x-axis and the terminal side to be somewhere else, this is the triangle that's going to make the most sense. Okay, so there's our angle theta, and we want the sine of theta to work this problem. And the sine of theta is opposite, which is -4, and a hypotenuse, which is 5. So looking at this triangle here, the sine of this angle is opposite -4 going down, and hypotenuse, which is 5. So y is going to be 5 times -4/5. Sorry, r was -5. We said that. R was -5. So -5 times -4/5, and the -5's cancel, and we get 4, which matches with what we had up here, right? Y was equal to 4. Okay, difficult problem because it was a non-standard angle. Let's do one more, and then we'll stop this tape. One more where let's see how much time we got running here. Oh, geez, we're going 18 minutes. We're going to stop this, and we'll do one more example that has a standard angle converting